So, hello everybody. Today the topic of discussion is UV visible spectra. Before this lecture we have discussed about what is a spectroscopy, or rather it was a lecture introducing spectroscopy. So, spectroscopy is when the or it is an interaction between electromagnetic radiation and matter. So, whenever electromagnetic radiation is going to fall on matter, what are the interactions which are going to take place between radiation and matter? So, that is dealt in spectroscopy, and in a spectroscopy basically we are going to concentrate on absorption spectra. And then one thing more here, in spectroscopy we are going to deal with, or basically we deal with energy changes in the matter or energy changes in the molecule when electromagnetic radiation falls with it. So, we are going to deal with different type of energies like rotational, vibrational, electronic. There is one more, translational, which is important in cases of gas. So, we are not going to take up for solids and liquids. With these energies we have got vibrational energy levels, and within these vibrational energy levels we study the transition. So, different spectra we are going to deal with different types of energies and different types of transitions. And another thing, the energy levels which are formed, they are all quantized. So, they are having a definite amount of energy. So, the next we start, this is the first absorption spectra, this is UV visible spectra, ultraviolet and visible spectra. So, although we are writing UV visible spectra, it is read also, or it is written as UV visible, but we are going to concentrate on UV spectra, which is an ultraviolet spectra. So, the range of ultraviolet spectra or UV visible spectra is given in terms of wavelength, nanometers. So, the range of UV spectra is from 200 nanometers to 340 nanometers. This range is of pure UV range. Then 340 to around 750 or 1000 nanometers. This is the visible range. So, if we talk about, if you are asked what is the UV range, then the UV range is from 200 to 340, and after 340 we have visible range. But if you are asked what is UV visible range, then it is from 200 to 750 or 1000 nanometers. So, this is the range. Now, what actually we deal with in UV spectra is electronic transitions. So, therefore, it is also known as electronic spectroscopy. So, UV spectra or UV is also known as electronic spectroscopy. By electronic spectroscopy we means that we are going to study electronic transitions. So, if this is one energy level and this is another energy level, and these are electronic energy levels. So, the transition from one energy level to another energy level is dealt in UV spectra. So, it is known as electronic spectroscopy. But as I told you in the last lecture that within vibrational energy levels, we are within electronic energy levels we are having large number of vibrational energy levels, and within vibrational energy levels we have got large number of rotational energy levels. So, one electronic transition is accompanied by large number of vibrational changes and large number of rotational changes. So, basically UV spectra is going to deal with electronic spectroscopy. That means it is going to deal with electronic transitions from one energy level to another. The next point is not all the spectra, or not all the molecules are going to give UV spectra. There are some of the molecules which give UV spectra, so they are UV active. The other molecules, they are not going to give UV spectra. Now, the molecules or the substance which give UV spectra are unsaturated compounds. So, this is a condition. Unsaturated compounds, they show UV spectra, whereas saturated compounds which are having only sigma bond, single bonded compounds, they are not going to give UV spectra. An unsaturated compound, if an unsaturated compound is having conjugation, then greater the conjugation, greater is the value of absorbance, wavelength at which the molecule is going to show absorption. So, the condition for UV spectra is given by the molecules which have got unsaturation with conjugation, and greater the conjugation, greater will be the wavelength at which the absorption is going to take place. For example, if I write these three compounds, one is CH3, CH2, CH3, the other is CH3, CH double bond, CH2, then I go with CH2, CH, CH double bond, CH2. Now, in these three compounds, this is a saturated compounds, which is it is only having single bond. So, this compound is not going to give UV spectra in any condition. Now, we have got these two compounds, both these compounds are saturated, unsaturated, but here we are not having conjugation, but here we are having conjugation. Conjugation is double bond, single bond, double bond, single bond, and so on. So, if we talk these two compounds, they are going to give UV spectra, but the wavelength at which this compound is going to show absorption, which will be higher in comparison to the absorption wavelength of this compound. Why? Because this here conjugation is there, and this compound, it is having only one double bond. So, conjugation is not there. So, greater the conjugation, greater is the wavelength for absorption of that particular compound. So, this is one important thing of UV spectra, that UV spectra is given by unsaturated compounds with conjugation, and greater the conjugation, greater is the wavelength for absorption. Next, we say that suppose these are two energy levels, as I draw E1 and E2. Now, electronic transition means electron is undergoing a transition from one energy level to another, and as I said, these energy levels are quantized. So, what should happen is, for every transition we should get a discrete line. Why? Because the energy levels are quantized and the transition is taking place between two quantized energy levels, but actually the condition is not like that. We are not getting a discrete line, but we get a band. So, this is the condition when the transition of electrons is taking place between two quantized energy level. Theoretically, we should get a discrete line. Why? Because for every transition we should get a discrete line. Why? Because the energy levels are quantized, but in experimentally or actually we are not getting discrete line for every transition. Instead, we get a band. So, why we are getting band is, with the one electronic transition is accompanied by large number of rotational changes and large number of vibrational changes. Because of that, these changes which are taking place along with the electronic changes, we are getting a band, we are not getting a discrete line. So, in UV spectra, we do not get a discrete line, instead we get a band. Why? Because with one electronic transition, we have large number of rotational changes and large number of vibrational changes. But if the same spectra is carried out in solutions, so what happens in solutions? In solution, we have a solute and we are going to have a solvent. So, you must have read in the chapter of solution in your 11th or 12th class that there is interaction between solute and solvent, there is interaction between solute and solute, and there is interaction between solvent and solvent. So, the same spectra where we were getting band is carried out in solutions, then we are not going to get this band, but we get discrete lines. Why? Because there are interaction between solute and solute, there are interaction between solvent and solvent, and there are interaction between solute and solvent. So we have got solute interaction, we have solvent interaction, and we have a solute solvent interaction. Because of the presence of these interactions, all the rotational changes and all the vibrational changes are restricted. They are not going to take place. So what is taking place is electron is undergoing transition from one quantized energy level to another quantized energy level. In that case, we are going to get this discrete line. So we are not going to get bands. Otherwise, if the spectra is not carried out in solutions, we are going to get a band. So this is how UV spectra is going to start up. So UV spectra, the range of UV spectra, exclusively of UV spectra, is 200 to 340 nanometers. Then it is an electronic spectroscopy where we deal with electronic transitions between quantized energy levels. But within electronic energy levels, we have large number of vibrational energy levels and we have large number of rotational energy level. So one electronic transition is accompanied by large number of rotational and vibrational changes. So whenever UV spectra is carried out, we get bands. We are not getting discrete lines. We get band because one electronic transition is accompanied by a large number of rotational or vibrational changes. But if the spectra is carried out in solutions we are already having these type of interactions. Interaction between solute and solute, solvent and solvent, and the third is solute and solvent. And because of these interactions within the solution, all the small changes, that is rotational and vibrational changes, they are restricted, and the only change which is going to take place is movement of electron from one energy level to another. So in that case we get discrete lines. Then UV spectra is only given by unsaturated compounds with conjugation, and greater the conjugation, greater is the wavelength of absorption. Then in UV spectra, we consider three types of electrons. So types of electrons. So we have three types of electron, or we are going to consider three types of electrons: sigma electrons, then second is pi electrons, and then is n electrons, which is non-bonding. So if we talk about bonds, then sigma bond is formed by head-long collision, pi bond is formed by sideways overlapping, and n electrons means they refer to lone pairs. So these are the three types of electrons which we are going to consider: sigma electrons, which are associated with saturated compounds, pi bonds which are associated with unsaturated compounds, and n electrons are present, they are associated with lone pair. So whenever there are elements like nitrogen, oxygen, sulfur or halogens, so any compound is having these elements, that means it is having n electrons, lone pairs or non-bonding electrons. With these electronic types of electrons, we have got four type of transitions. So the next is types of transitions. So if we draw the transitions, these are energy levels which I am drawing. So this is sigma, pi, n, pi star, sigma star. So, with these three types of electrons, we have got 4 types of transitions which can take place. The first transition is from sigma to sigma star. So, this is the first transition which is going to take place, sigma to sigma star. So, I should write here, this is the transition, sigma to sigma star. The second transition is N to sigma star transition. So, N to sigma star transition, this is the transition, N to sigma star. Then the third transition is N to pi star transition. So, N to pi star means this is the transition, N to pi star, and the last transition is pi to pi star transition. So, pi to pi star is, this is the transition, pi to pi star. So, with this, if we have 3 types of electrons, that is N, sigma, pi electrons, sigma electrons and an electrons. With these 3 electrons, we are going to have these 4 type of transitions, sigma to sigma, then we have N to sigma, N to pi, and the last is pi to pi star. So, if we take up the transitions one by one, this one, first one, sigma to sigma star. So, sigma, the transition is from sigma to sigma star, that means it is given by saturated compounds. So, because it is given by saturated compounds and UV spectra is only given by unsaturated compound. So, this transition, for this transition to take place, the energy which is required is not going to lie in UV range. So, this transition is not going to lie in the UV range, and the wavelength for this transition is 126 nanometers to 136 nanometers, and the UV range starts from 200 nanometers. So, this transition sigma to sigma star is not lying in the UV range, and it is given by pure saturated compound, and UV spectra is given by unsaturated compound. Next we come to N to sigma star transition. Now, this type of transition is given by saturated compounds having lone pairs. So, any saturated compound which is having groups like nitrogen, oxygen, sulfur or halogens, such compounds are going to show this transition. The range of this transition is around 180 nanometers. So, again it is also still not in the UV range, but it is close to the UV range because our UV range is going to start from 200. So, this is the second transition. The third transition is N to pi star. It is given by, because pi, now the pi bond is pi orbital is involved, that means it is unsaturated compound. So, any unsaturated compound having these elements, so unsaturated compound with lone pair of electrons is going to give this transition N to pi star. Now, what happens is, non-bonding orbital and pi bonding orbitals, they are perpendicular to each other. So, because they are perpendicular to each other, so the transition of electron is difficult. So, this transition N to pi star is having very low intensity. So, if we talk in terms of intensity, then this transition N to pi star, the intensity of this transition is very low, and it is low because N bonding, N orbitals, non-bonding orbitals and pi orbitals, they are perpendicular to each other, and because they are perpendicular to each other, so the transition of electron becomes difficult. The fourth transition is pi to pi star. So, pi to pi star means it is given by pure unsaturated compounds which are having double bonds or which are having triple bonds. So, if the bond is this, or if the bond is this, both these compounds they are going to, so they will show this type of transition which is pi to pi star. So, with the three types of electrons, we have got these 4 type of transition. I repeat, sigma to sigma star transition is given by saturated compound. The range is 120. This is a 126 to 136, and this transition is not going to lie in the UV range. Another reason we can say that it is of very high energy, so this is not going to lie in the UV range. Then the second transition is N to sigma star. It is given by saturated compounds having lone pairs, and the range is 180, so it is near to the UV range. The third transition is N to pi star, which is given by unsaturated compounds having lone pair. This transition, the third one, is of lowest intensity. Why? Because n orbital and pi orbitals, they are perpendicular to each other, so the transition of electron becomes difficult. And the last one is pi to pi star. This transition is given by pure unsaturated compounds. So, intensity of this transition is low. If we talk about in terms of energy, then this is of highest energy, then we have this, third is this, and fourth is this one. That is in terms of energy, because here the transition is between pi to pi star. So, this is all about the transitions in UV spectra. Now, with transition, we come to another important principle in UV spectra, which is Franck-Cordon principle. Franck-Cordon principle. So, here I am going to discuss what is the ideal situation and what actually is happening when the electronic transitions are taking place. So, the ideal situation is this. This is E1, which is the lower energy levels, and within this we are having vibrational and rotational energies, and then this is E2, and again these are vibrational and rotational changes. So, what is happening is, this is lower energy level and this should be the higher energy level, and electrons, they undergo transition from one energy level to another energy level. So, this should be the ideal situation. What is this? And the plot which I have drawn is between energy and internuclear distance. This is internuclear distance. So, this is the ideal situation. The upper energy level is just above the lower energy level. So, this is the ideal situation whenever electronic transitions are taking place, but actually the scene is something else. The scene is, this is the lower energy level, which is E1, and this is the higher energy level, which is E2. Again, this is potential energy and this is internuclear distance. So, as it is very visible that the higher energy level is not, or lower energy level is not below the higher energy level, but higher energy level is present at a higher internuclear distance in comparison to the lower energy level. That is Franck-Cordon principle. The higher energy level is present at a higher internuclear distance in comparison to the lower energy level. So, this is Franck-Cordon principle. Now, the reason behind this is, as we say that suppose an atom is undergoing a transition from one energy level to another. In atom we have got electrons and we are having nucleus. So, as the electrons they move, because the mass of electron is 0, lighter, and nucleus is not light, it is having a mass. So, as there is a transition from one energy level to another, electron being lighter is going to flip itself. So, the state is changed, the spin is changed or the properties are going to change. So, electrons undergoes the change very easily because it is lighter, but for nucleus is not going to change so abruptly. It takes time for changing itself. So, when the atom undergoes transition and it comes to this higher energy state, the electron has changed or adjusted itself according to the energy of this energy level, but nucleus is still present in the grounds, the state at which it was present in E1. So, here in this state electron has changed itself, but nucleus has not changed. So, what happens in higher energy state? The bonding between electron and nucleus, it becomes loose. So, because it becomes loose, so that is going to occur at a higher internuclear distance. So, the position and the velocity during the transition, the position and velocity of the nucleus is not undergoing a change. And what is happening because of this? The upper energy state occurs at a higher internuclear distance. That is Frank-Codon principle. So, this is an important consideration when we are going to deal with the electronic changes. So, this is all about Frank-Codon principle. Next, in UV spectra we have got some two important types of actually compounds. One is chromophore and other is oxochrome. So, if I explain you with an example, then suppose I am taking up this molecule. This is 1,3-butadiene. It is having it is an unsaturated compound with 2 double bonds at first and third carbon. So, it is going to give UV spectra, pure UV spectra. Now, what happens is chromophores, if chromophores are the compound, they are covalently bonded compound. If they are added to an unsaturated system, then the position of double bonds, they become colored. So, this portion will become colored as well as this portion will become colored. So, whenever chromophores are added to an unsaturated compound, then the position of the double bond or unsaturation, they become colored. So, what does it infer? It is going to tell us about whether the compound is saturated or it is unsaturated, and if it is unsaturated, then where the unsaturations are present. So, this helps in analysis of the compound. So, whenever a chromophore is an covalently bonded compound, which when added to an unsaturated compound shows or makes the double bonds colored, or the position of the double bond colored. That is the function of chromophores. Now, we have got two types of chromophores. One is pi bonded or having pi electrons, and another one having n electrons. So, pi electrons means this is an example of pi electrons. N electrons means if we are having a carbonyl group or we are having a cyanide group. These are going to function as chromophores. Now, if we are having these two types of compounds, then the transitions which take place here will be n to pi star. Sigma and sigma star is always going to take place, because if we take up any molecule, sigma bond is always present. So, here the first transition is sigma to sigma star and the second transition is n to sigma star. Similarly, in this compound. So, these are two types of chromophores, one having only pi electron, the other having n electrons, and n electrons, these are the two examples. So, chromophores, what is the function of chromophores? It is a covalently bonded compound which is going to impart color to the unsaturated bonds. So, wherever unsaturation is there, that bond is going to become colored. So, we can identify where the unsaturation is present in the molecule and how many double bonds are there. So, that is the function of chromophore. Now, if I talk about oxochrome, if I add suppose this is again I am taking up the same example. If I add oxochrome directly to this double bonded compound, it is not going to show any kind of effect. So, oxochrome as such has no property which is useful in UV spectra, but if I add oxochrome to chromophore and then I add this chromophore to the double bonded compound, now the changes are going to take place, and that is the changes are known as UV shift. So, oxochrome as such they show no property of interest in UV spectra, because if they are adding directly to the unsaturated compound, no effect is absorbed. But if oxochrome is added to chromophore and then chromophore is added to this unsaturated compound, then we have got certain shifts in this in the absorption band. So, and the shifts which take place, we are going to deal with that. So, suppose this is the absorption spectra, this is energy and this is psi. So, this is an absorption band which is obtained because of any compound. So, to this compound if I add oxochrome to chromophore, then and that chromophore is added to the unsaturated compounds, we have got 4 shifts, and these shifts are known as UV shifts. So, UV shifts. So, actually what are the UV shift? When an oxochrome is added to chromophore and then the chromophore is added to an unsaturated compound, some shifts are going to take place, and they are known as UV shift. Now, the first shift which takes place is bathochromic shift. Now, bathochromic shift means the absorption maxima is going to shift towards higher wavelength. So, this is actually wavelength. So, higher wavelength, that is bathochromic shift. So, the shifting of absorption maxima to a higher wavelength is bathochromic shift. So, whenever an oxochrome is added to a chromophore and then that chromophore is added into the unsaturated compound, one shift which is possible is bathochromic shift. That means the wavelength, this absorption maxima is shifted towards the higher wavelength. This is why this is happening is the compound or the oxochrome which is added is increasing the conjugation, and because it is increasing the conjugation, the maxima is obtained at a higher wavelength. So, this is the reason why this is happening. The second is hypsochromic shift. Hypsochromic shift means the absorption maxima is shifted towards shorter wavelength. This is hypsochromic shift. So, if the maxima is shifted towards shorter wavelength, that means the conjugation, any compound, this is a compound which is going to decrease the conjugation. So, the lambda max is shifted towards shorter wavelength. The third type of effect when we add oxochrome to a chromophore is hyperchromic shift. When we talk about hyperchromic shift, that means the intensity of absorption is going to increase. Hyperchromic. the intensity of absorption is going to increase. And the fourth is hypochromic. Hypochromic, as you can make out, the intensity here is going to decrease. This is hypochromic shift. So these are the 4 shifts which are going to take place in the absorption band when an oxochrome is added to a chromophore. And the example of oxochrome can be an OH group or OR group. There are many such examples. These are two of them. So these are the 2 important compounds, oxochromes and chromophores. So oxochromes, they are the covalently bonded compound which impart color to an unsaturated bond, or it is going to impart color to a double bond. So it helps us to predict where the double bond is present and how many double bonds are present in a given compound. Oxochrome as such, they have no property. So when an oxochrome is added to an unsaturated compound, no effect is going to take place. But if an oxochrome is added to a chromophore and then it is added to an unsaturated compound, then these are the shifts which are going to take place. So these are 4 shifts. Either the absorption maxima is going to increase or it is going to decrease, or the wavelength of absorption is increasing or the wavelength of absorption is decreasing. When the absorption wavelength increases, that is bathochromic shift. If it is decreasing, it is hypsochromic. If the intensity of absorption is increasing, it is hyperchromic, and if the intensity is decreasing, it is hypochromic. So these are the effects, these are the 4 shifts, and they are also known as UV shift. And after this, we have certain applications of UV spectra. So the last is applications. The first application of UV spectra is it helps in qualitative analysis. By qualitative analysis means it is going to tell us about the quality of the compound. Quality of the compound is first thing which we can distinguish or we can know on the basis of UV spectra is whether the compound is saturated or it is unsaturated. So if the compound is saturated, it is not going to give UV spectra, and if the compound is unsaturated, it is going to give UV spectra. And the second thing, it also tells us about the extent of conjugation. How much conjugation is there? So it is going to tell us about the extent of conjugation. If a molecule or a substance is having extended conjugation, then the wavelength of absorption is going to increase. So greater the conjugation, greater is the wavelength for absorption. So it is going to tell us about the extent of conjugation. Then we can identify how many double bonds are present and what is the position of the unsaturation or double bond. So it tells us about the position of double bond. So how can we know the position? To an unsaturated compound, I am going to add up chromophores. So when I add chromophores, the position of the double bonds, they become colored. So it is going to tell the position as well as how many double bonds are there. And if I add oxochrome to the chromophores, then I have got 4 shifts which I have already discussed, that are bathochromic, hyperchromic, hypsochromic and hypochromic shift. Wavelength is either going to increase or it is going to decrease. The intensity of absorption maxima is either going to increase or it is going to decrease. So it tells us about the position of the double bond. Fourth thing it tells is the impurity. Whether the impurities are present in the compound or they are not present. Suppose if I get this is some spectra which is obtained because of the UV spectra. This is the UV spectra which is carried out. Now what happens if this is the UV spectra and one of the bands is of higher intensity, that means you can see it very clearly. So the band can be seen very clearly or it is highly intense. That means that that intense band is because of the presence of an impurity. So by UV spectra we can find out the impurity, if any impurity is present in the particular compound. And how can we find out? The band which is obtained because of impurity is highly intense band. So these are the qualitative analysis. We can find out the quality of the compound. First is whether the compound is saturated or unsaturated. The extent of conjugation can be determined. The position and number of double bonds can be determined. And the last, it can determine the impurity if present in the molecule. Next we have quantitative analysis. Quantitative analysis. By quantitative analysis means I can determine the concentration, and that is done by Beer's law, which I discussed in the last lecture of introduction to spectroscopy. And Beer's law is A is equal to epsilon CL. So if I know the absorbance, if I know the path length, if I know the molar extension coefficient, I can determine the concentration. So I can, this is quantitative analysis. So it helps us to determine the concentration, and with concentration, when concentration is multiplied by molecular weight, I can determine the solubility, and it also helps us to determine the molecular weight. How can I determine the molecular weight? Because if I know the concentration, then I can determine molarity, normality. If I know this, then molecular weight can be determined very easily. Third thing, it helps us to determine the reaction or the constants or equilibrium constant of an acid or a base. So it helps us to determine equilibrium constant or dissociation constant. Dissociation constant either of an acid or of a base. So these are some of the applications. It helps us in qualitative analysis, it helps to determine, it helps in quantitative analysis, it can help us to determine the molecular weight of the compound, it helps us to determine the dissociation constant of either acid or a base. So these are the applications of UV spectra. So if I summarize the whole UV spectra, then UV spectra, the range of exclusively UV spectra is 200 to 340 nanometers. It is electronic spectroscopy because here we study electronic transitions from one energy level to another. And it is given by unsaturated compounds with conjugation, and greater the conjugation, greater is the absorption wavelength. Then whenever transition is taking place, the energy levels are quantized. So with this effect, we think that every transition, for every transition discrete lines should be obtained, but actually every transition we are not getting discrete lines, instead we get a band. We are getting the band because every electronic transition is accompanied by large number of rotational changes and large number of vibrational changes. Because of this we are getting a band, we are not getting discrete lines. But if the same spectra is carried out in solutions, then all the vibrational and rotational changes are restricted. Why? Because there is an interaction between solute and solute, solvent and solvent, and there is an interaction between solute and solvent. Because of this, all the small changes are restricted. In that case, we get discrete lines. Then in UV spectra, we consider three types of electrons, sigma, pi and n. With this we have 4 types of transitions: sigma to sigma star, N to sigma star, N to pi star and pi to pi star transitions. Then we have got 2 types of compounds in the important compounds in UV spectra. One is chromophore, the other is oxochrome. Chromophores, they are covalently bonded compounds, and if they are added to an unsaturated compound, then it imparts color to the double bond or unsaturation. With this we can find out where the double bonds are present in the molecules and how many double bonds are there. If we come to oxochrome, oxochrome as such has no properties, but when oxochrome is added to a chromophore, then it intensifies the property of chromophores, leading to 4 type of shifts, and they are known as UV shifts: bathochromic shift, hypsochromic shift, hyperchromic shift and hypochromic shift. So these are the 4 UV shift which take place when oxochrome is added to a chromophore. And the last, we were having applications. It helps us in qualitative analysis whether the compound is saturated, unsaturated, what is the position of the double bond, how many double bonds are there, if impurity is present or the molecule is pure. So all these things can be dealt in qualitative analysis. Then we have quantitative analysis, which can be done by Beer's law. We can determine the concentration. Then it helps us to determine the molecular weight, because we can know concentration by Beer's law, so we can determine the molecular weight. And the last application is it helps us to calculate the dissociation constant of an acid or a base. So this is all in UV spectra. Thank you.